Section 1. The hidden language of the human brain, how thought becomes signal. The human brain is not a silent organ. Even in complete stillness, when the body does nothing and the eyes are closed, billions of neurons are firing in precise electrochemical patterns. Every thought, memory, emotion, and intention is encoded not as words or images, but as changes in voltage, ion flow, and timing across vast neural networks. For most of human history, this internal language was inaccessible, locked inside the skull, invisible and unreadable. Brain-computer interfaces exist because modern science discovered that thoughts are not abstract. They are measurable physical events. At the most fundamental level, the brain operates as a biological electrical system. Neurons communicate through action potentials, brief spikes in voltage caused by the movement of sodium and potassium ions across cell membranes. These spikes are not random. They occur in patterns, frequencies, and sequences that carry information. When you decide to move your hand, neurons in the motor cortex fire milliseconds before the movement occurs. When you remember a face, specific neural assemblies in the temporal lobe reactivate stored patterns. The brain does not store information in single neurons, but in distributed populations that fire together, a principle known as population coding. This realization changed neuroscience permanently. If thoughts are encoded as electrical activity, then in theory, machines can read them provided the signals can be captured, amplified, and decoded. This is the foundational idea behind brain-computer interfaces. A BCI does not read thoughts in a human sense. It detects neural signals associated with intention, perception, or movement and translates them into machine-readable commands. The challenge is not whether thoughts exist physically, but whether technology is precise enough to interpret them reliably. Early experiments in the mid-20th century proved this was possible. In the 1960s, neuroscientists discovered that monkeys could be trained to control cursors using only neural activity recorded from their motor cortex. These experiments demonstrated a critical principle: the brain can adapt to external devices. When feedback is provided, neural circuits reorganize themselves to control new tools, even ones not part of the body. This ability is known as neuroplasticity, and it is one of the most important biological mechanisms enabling brain-machine communication. Neuroplasticity means the brain is not fixed. Neural connections strengthen, weaken, or reroute in response to experience. When a person learns to use a BCI, they are not forcing a machine to understand the brain alone. The brain is also learning how to speak to the machine. Over time, neural firing patterns become more stable, more efficient, and more predictable. This mutual adaptation is why long-term BCI users can achieve levels of control that appear almost effortless, such as moving robotic limbs or typing text with thought alone. To capture neural signals, however, the brain must be observed at extraordinary resolution. The electrical signals produced by neurons are extremely weak, often measured in microvolts, and easily distorted by noise from muscles, the environment, or even the skull itself. This led to the development of multiple signal acquisition strategies, ranging from non-invasive to highly invasive methods. Each approach represents a trade-off between safety, precision, and information bandwidth. Non-invasive systems, such as electroencephalography (EEG), place electrodes on the scalp to detect synchronized neural activity across large populations of neurons. EEG is safe and widely used, but its spatial resolution is limited. The skull acts as a filter, blurring signals and making it difficult to isolate activity from specific brain regions. Despite this, EEG-based BCIs have enabled paralyzed patients to select letters, control wheelchairs, and interact with digital environments using mental effort alone. Invasive approaches, by contrast, place electrodes directly on or inside the brain tissue. These systems can detect activity from individual neurons or small neural clusters, providing far richer data. Technologies such as intracortical microelectrode arrays record signals with millisecond precision, capturing the fine-grained dynamics of neural firing. This level of detail allows machines to decode complex intentions, such as multi-dimensional hand movements or speech, articulation patterns. The decision to use invasive interfaces is not taken lightly. Implanting electrodes requires neurosurgery, introduces risks of infection, inflammation, and long-term tissue response. Over time, the brain may encapsulate electrodes with scar tissue, degrading signal quality. Modern BCI research focuses heavily on materials science, developing flexible, biocompatible electrodes that move with the brain and minimize immune response. The goal is long-term stability, not short-lived experiments. Once neural signals are captured, they must be transformed into usable data. Raw brain signals are chaotic, noisy, and high-dimensional. Advanced signal processing techniques filter out irrelevant activity, isolate meaningful patterns, and extract features such as firing rate, oscillation frequency, and temporal correlations. These features are then fed into machine learning models trained to associate specific neural patterns with specific outcomes such as moving a cursor left, selecting a word, or generating synthesized speech. This is where artificial intelligence becomes inseparable from brain-computer interfaces. The human brain does not communicate in discrete commands. It operates probabilistically, with overlapping signals and constant variability. Traditional rule-based systems cannot handle this complexity. Modern BCIs rely on deep learning, neural networks, and adaptive algorithms that improve over time. As more data is collected, the system becomes better at predicting user intent, reducing error rates and latency. Latency is critical. For a BCI to feel natural, the delay between thought and action must be extremely small, often less than 100 milliseconds. Delays longer than this break the illusion of control and increase cognitive load. Achieving low latency requires optimization across hardware, software, and neural decoding pipelines. This is one reason why BCI research is deeply interdisciplinary, combining neuroscience, electrical engineering, computer science, materials science, and cognitive psychology. Importantly, BCIs do not bypass consciousness. They do not read hidden thoughts or subconscious desires. They operate on measurable neural correlates of intention, usually requiring deliberate mental effort. A person must intend to move, select, or communicate. The machine interprets patterns associated with that intention, not abstract ideas or emotions. This distinction is essential for understanding both the power and the limitations of brain-machine technology. Yet even with these limitations, the implications are profound. Once thought can be converted into signal, and signal into action, the boundary between biological intelligence and artificial systems begins to dissolve. Machines no longer require keyboards, touchscreens, or voice commands. The brain itself becomes the interface. This shift represents not just a technological advancement, but a fundamental change in how humans interact with machines. As this documentary progresses, we will move deeper from the biology of neurons to the algorithms that decode them, from medical breakthroughs to ethical dilemmas, and from experimental laboratories to global infrastructure risks. But everything begins here, with a simple yet unsettling truth. The human mind speaks in electricity, and technology has learned how to listen. Section 2. How electrodes talk to neurons. The physics, biology, and limits of neural signal capture. If thoughts are electrical, then the most critical challenge in brain-computer interfaces is not decoding, but listening. The human brain is one of the noisiest electrical environments known in biology. Every heartbeat, every eye movement, every muscle contraction produces electrical interference. Even the brain itself generates overlapping rhythms that can mask the signal of interest. Extracting meaningful neural data from this environment is not a matter of simple measurement. It is a problem of physics, materials science, and biological compatibility operating at microscopic scales. At the center of this challenge lies the electrode. An electrode is not merely a wire, it is a transducer, a device that converts ionic currents in biological tissue into electronic currents usable by machines. Neurons communicate using ions such as sodium, potassium, calcium, and chloride. Computers, by contrast, operate using electrons flowing through metal and silicon. The electrode must bridge these two fundamentally different worlds without distorting, destroying, or overwhelming the signal. When an electrode is placed near a neuron, it does not record thoughts directly. Instead, it detects voltage changes in the extracellular space caused by nearby neurons firing action potentials. These voltage changes are extraordinarily small, often measured in tens of microvolts. To put this in perspective, everyday electronic noise from power lines or radio signals can be thousands of times stronger. This is why electrode placement, impedance, surface chemistry, and geometry are critical factors in BCI performance. Non-invasive electrodes, such as those used in electroencephalography, sit on the scalp and measure the summed activity of millions of neurons firing synchronously. The skull, however, is a poor conductor. It attenuates high-frequency signals and spatially smears neural activity. As a result, EEG provides excellent temporal resolution, detecting changes on the order of milliseconds but limited spatial resolution. Signals originating from different brain regions can overlap, making precise decoding difficult. Despite these limitations, non-invasive BCIs remain essential. They are safe, scalable, and suitable for widespread use. EEG-based systems have enabled stroke patients to regain basic communication, allowed users to control drones and robotic arms, and even facilitated limited brain-to-brain communication experiments. Advances in dry electrodes, adaptive filtering, and AI-driven signal separation continue to improve their performance. However, they remain fundamentally constrained by physics. The farther the electrode is from the neuron, the less information it can capture. Invasive electrodes take a radically different approach. By placing sensors directly on the cortical surface or penetrating into brain tissue, they bypass the skull entirely. Electrocorticography, or ECG, places electrode grids on the surface of the brain beneath the skull. These electrodes capture signals with far higher amplitude and spatial specificity than EEG, while remaining less damaging than deep implants. ECG has been particularly successful in decoding speech-related neural activity, enabling paralyzed individuals to generate synthesized speech from brain signals alone. Going deeper still are intracortical microelectrodes. These devices penetrate the brain tissue itself and record activity from individual neurons or small neural clusters. At this level, the richness of information increases dramatically. Researchers can observe precise firing patterns, correlate them with intended movements, and decode complex motor trajectories in real time. This is the technology behind some of the most advanced prosthetic control systems ever developed. However, the closer technology moves to neurons, the more biology pushes back. The brain is not passive tissue. It reacts to foreign objects with inflammation and immune responses. Over time, glial cells form a barrier around implanted electrodes, increasing impedance and degrading signal quality. This phenomenon, known as the foreign body response, is one of the greatest obstacles to long-term invasive BCIs. Signals that are clear in the first months after implantation can fade over years. To address this, researchers are rethinking electrode design from the atomic level upward. Traditional rigid electrodes made of silicon or metal create mechanical mismatch with the soft, gelatinous brain tissue. Every heartbeat causes the brain to move slightly, generating micro-damage around stiff implants. Modern designs favor flexible polymers, ultra-thin filaments, and mesh-like structures that move with the brain rather than against it. Some experimental electrodes are thinner than a human hair, reducing tissue displacement and inflammation. Material choice is equally critical. Electrodes must be conductive, biocompatible, and chemically stable. Gold, platinum, iridium oxide, and graphene are commonly used due to their favorable electrical properties and resistance to corrosion. Surface modifications increase effective surface area at the nanoscale, reducing impedance and improving signal-to-noise ratio. In essence, the electrode becomes less of a probe and more of an extension of the neural environment. Another fundamental issue is bandwidth. The brain does not communicate in a single frequency. Neural signals span a wide spectrum, from slow oscillations associated with sleep and attention to high-frequency spikes encoding precise motor commands. Capturing this full spectrum requires electrodes and amplifiers capable of handling massive data throughput. A single implanted array can generate gigabytes of data per day. Managing, transmitting, and processing this data in real time is a major engineering challenge. Wireless transmission adds another layer of complexity. Wired connections increase infection risk and limit mobility. Modern BCIs increasingly rely on wireless data links and implanted power systems. These must operate safely within the body, generating minimal heat and resisting electromagnetic interference. Power efficiency becomes a life-or-death concern. Excess heat can damage neural tissue, while insufficient power degrades performance. As electrodes improve, a deeper realization has emerged. No electrode is neutral. The act of measurement itself alters neural activity. Electrodes can stimulate neurons unintentionally, change local electric fields, or bias which signals are recorded. This creates a feedback loop between brain and machine that must be carefully managed. Some advanced systems intentionally exploit this effect, using the same electrodes for both recording and stimulation to shape neural activity in beneficial ways. This dual capability, reading and writing to the brain, marks a turning point. Electrical stimulation can restore lost function, suppress pathological activity, or enhance plasticity. Deep brain stimulation already treats Parkinson's disease and epilepsy. In BCI systems, stimulation can provide sensory feedback to users, allowing prosthetic limbs to feel pressure or texture. The brain begins to incorporate artificial signals as if they were natural sensations. Yet this raises profound scientific and ethical questions. When electrodes modify neural circuits, where does control truly reside? Is the brain adapting to the machine, or is the machine reshaping the brain? In practice, both occur simultaneously. Neuroplasticity ensures that prolonged interaction with BCIs leads to lasting changes in neural organization. These changes can be beneficial, but they are not fully reversible or predictable. By the end of this section, one truth becomes unavoidable. The electrode is not just a sensor, it is a gateway. It defines how much of the brain machines can access, how safely, and for how long. Every limitation in BCI technology today, speed, accuracy, scalability, can be traced back to the physics and biology of signal capture. In the next section, we will move beyond hardware and into interpretation. Once neural signals are captured, how does a machine understand them? How does noise become meaning? How does intention become action? This is where artificial intelligence takes center stage, and where the brain's complexity collides with algorithms designed to learn. Section 3. Decoding the brain. How machines learn to translate neural activity into meaning. Once neural signals are captured by electrodes, the greatest challenge begins. Raw brain data is not language. It is not commands. It is not intention. It is a chaotic mixture of voltage fluctuations, oscillations, spikes, noise, and biological variability. Turning this raw electrical activity into meaningful output is one of the most complex inverse problems ever attempted in science. The brain does not label its signals. There is no inherent marker that says this pattern means move the hand or this activity represents a word. Meaning must be inferred, learned, and continuously adapted. At the heart of neural decoding lies the concept of population coding. Individual neurons are unreliable. A single neuron may fire differently from one moment to the next even when the same action is intended. The brain compensates by encoding information across large populations of neurons. Meaning emerges statistically, not deterministically. This forces machines to abandon classical rule-based programming and instead adopt probabilistic and learning-based approaches. Early brain-computer interfaces relied on linear decoding models. Researchers assumed that specific features of neural signals such as firing rate or oscillation amplitude mapped directly to motor output. These models worked in controlled environments, but failed under real-world variability. The brain is non-linear, context-dependent, and constantly changing. Decoders that assume static relationships inevitably degrade over time. This realization drove the adoption of machine learning. Rather than specifying how neural signals should be interpreted, researchers allowed algorithms to discover patterns on their own. Supervised learning became the dominant paradigm. Users were asked to perform or imagine actions while neural data was recorded. The machine learned correlations between signal patterns and known outcomes. Over time, the decoder improved its predictions. However, supervised learning exposes a fundamental limitation. The brain does not produce identical signals twice. Neural activity drifts due to fatigue, learning, emotional state, and even circadian rhythms. Electrodes shift microscopically. Tissue responses change signal characteristics. As a result, decoders trained on yesterday's data may fail today. This phenomenon, known as non-stationarity, is one of the central obstacles to stable BCIs. To counter this, modern systems employ adaptive decoding. The decoder itself learns continuously, updating its parameters in real time. This creates a closed-loop system in which both the brain and the machine adapt to each other. The user learns how to modulate neural activity more effectively, while the algorithm learns to interpret subtle changes more accurately. This co-adaptation is not optional. It is essential for long-term performance. Deep learning dramatically accelerated progress in this area. Neural networks, ironically inspired by the brain itself, excel at extracting structure from high-dimensional data. Convolutional networks identify spatial patterns across electrode arrays. Recurrent networks capture temporal dependencies in neural firing. Transformer-based architectures, originally designed for language, are increasingly used to model long-range neural correlations. These models do not decode neurons individually. They operate on ensembles, learning distributed representations that reflect intent, movement trajectories, or speech phonemes. In speech BCIs, for example, decoders learn to map neural activity in motor speech areas to articulatory features rather than directly to words. This mirrors how the brain itself organizes speech, increasing decoding accuracy and robustness. One of the most striking achievements in recent years has been the decoding of imagined speech. Individuals unable to speak due to paralysis have produced intelligible sentences using only neural activity. This was not achieved by reading thoughts directly, but by decoding the motor plans for speech that the brain still generates even when muscles cannot execute them. This distinction is critical, BCIs read intention expressed through neural pathways, not abstract conscious experience. Despite these advances, decoding remains probabilistic. There is no perfect translation. Errors are inevitable, and systems must be designed to handle uncertainty. Confidence estimation becomes as important as prediction itself. In high-stakes applications, such as medical devices, incorrect decoding can have serious consequences. This is why modern BCIs integrate error detection and correction mechanisms, often involving the user's own feedback. Another emerging approach is unsupervised and self-supervised learning. Instead of relying on labeled data, algorithms learn the intrinsic structure of neural signals. This is particularly valuable when explicit training data is unavailable or when signals drift over time. By learning stable latent representations, decoders can generalize better and require less retraining. Yet even the most advanced AI faces a hard boundary. Meaning is contextual. The same neural pattern can represent different intentions depending on task, environment, or internal state. Contextual decoding requires integrating neural data with external information, such as sensory input, task constraints, and behavioral history. This pushes BCIs toward multimodal architectures that combine brain signals with vision, audio, and environmental sensors. Latency is another critical factor. The brain operates on millisecond timescales. Delays introduced by signal processing or model inference can disrupt the sense of agency. If a prosthetic arm responds too slowly, the brain perceives it as external rather than embodied. Achieving real-time decoding with minimal latency requires optimized hardware, efficient algorithms, and sometimes on-device inference within implanted systems. A deeper philosophical challenge underlies all decoding efforts. The brain does not encode information in a fixed codebook. Neural representations are dynamic and task-specific. Unlike digital communication systems, there is no universal neural language. Every brain is unique. Even within the same individual, representations evolve through learning and plasticity. This makes generalized decoders extraordinarily difficult to build. Some researchers propose that instead of forcing machines to decode the brain, we should allow the brain to learn the machine. In this paradigm, the decoder provides a simple, stable mapping, and the brain adapts its activity to control the interface. This approach leverages the brain's remarkable plasticity and may offer greater long-term stability, albeit with slower initial learning. As decoding technology improves, a new possibility emerges: bidirectional intelligence. The same models used to interpret neural signals can predict how stimulation will affect neural activity. This enables closed-loop modulation, where the system not only reads intention, but actively shapes neural dynamics to optimize performance or restore function. The boundary between decoding and control begins to blur. By the end of this section, it becomes clear that the intelligence of a brain-computer interface does not reside in electrodes or processors alone. It emerges from the interaction between biological learning and artificial learning. The machine does not replace the brain. It becomes a partner in an adaptive system whose behavior cannot be fully attributed to either component alone. In the next section, we will explore how the brain changes itself in response to this partnership. How does prolonged interaction with machines reshape neural circuits? How does neuroplasticity enable embodiment of artificial devices? And where are the limits of adaptation before biology resists further integration? Section 4. When the brain adapts. Neuroplasticity and the embodiment of machines. The most profound discovery in modern neuroscience is not that the brain can control machines, but that it can come to accept them as part of itself. This capacity, known as neuroplasticity, is the biological foundation that makes long-term brain-computer integration possible. Without plasticity, BCIs would remain fragile tools requiring constant recalibration. With plasticity, they become extensions of the nervous system. Neuroplasticity refers to the brain's ability to reorganize its structure, function, and connectivity in response to experience. Neurons alter their firing patterns, synaptic strengths change, and entire cortical regions can be reassigned to new functions. This is not a rare or exceptional phenomenon. It is how the brain learns, recovers from injury, and adapts to the body it inhabits. Brain-machine interfaces exploit the same mechanism, but in a context evolution never prepared for. When a person begins using a BCI, the brain initially treats the device as external. Neural signals are inconsistent, effortful, and cognitively demanding. Control feels indirect, similar to learning a new tool. Over time, however, repeated interaction reshapes neural circuits. Activity becomes more stable, representations become more efficient, and control transitions from conscious effort to automatic execution. This is not merely learning the interface. It is the brain rewriting itself to incorporate the interface. One of the clearest demonstrations of this process comes from motor cortex studies. When individuals control robotic arms through BCIs, neurons that once encoded natural limb movements begin to encode the dynamics of the artificial device. Importantly, the brain does not maintain separate representations for biological and artificial limbs. It optimizes for control. If the machine responds consistently, the brain adopts it into its internal model of the body. This internal model, often referred to as the body schema, is a continuously updated neural representation of the body's shape, position, and capabilities. The body schema is not fixed. It expands to include tools, as seen when using a tennis racket or driving a car. In BCI users, this expansion can occur at a much deeper level, incorporating devices that are controlled directly by neural activity rather than through muscles. Embodiment occurs when the brain predicts the sensory consequences of an action and receives matching feedback. In natural movement, motor commands generate expected sensory input from muscles and skin. When BCIs provide appropriate feedback, visual, tactile, or electrical, the brain begins to treat the artificial output as self-generated. This prediction feedback loop is critical. Without feedback, control remains abstract and fragile. With feedback, it becomes intuitive. Sensory feedback is therefore not optional. It is essential. Early BCIs relied solely on visual feedback, forcing users to constantly watch their actions. This places a heavy cognitive load on attention systems. More advanced interfaces introduce somatosensory feedback through electrical stimulation of sensory cortex or peripheral nerves. These signals do not replicate natural sensation perfectly, but the brain does not require perfect fidelity. It requires consistency. Given stable patterns, the brain learns to interpret artificial signals as meaningful sensory input. Remarkably, sensory remapping can occur even when feedback is delivered to unexpected cortical locations. Stimulating one area of the sensory cortex can produce perceived sensations in entirely different body parts if the brain learns the association. This flexibility reveals a critical truth. Sensation is not hardwired. It is constructed. The brain assigns meaning to signals based on experience, not origin. Neuroplasticity also operates at the level of timing. Neural circuits adapt to delays introduced by BCIs. When latency is consistent, the brain recalibrates its predictions to account for it. This temporal adaptation allows users to experience a sense of agency even when machine response is slower than biological movement. However, there are limits. Variable or unpredictable delays disrupt embodiment and degrade performance. Plasticity is not uniform across the brain or across the lifespan. Younger brains adapt more rapidly, but adult brains retain substantial plastic potential. However, prolonged use of BCIs can lead to structural changes that are not easily reversed. Cortical maps can reorganize permanently. This raises important questions about long-term consequences, particularly when interfaces are used for enhancement rather than restoration. The brain's capacity to adapt is not infinite. Plasticity operates within biological constraints imposed by metabolic cost, structural connectivity, and genetic factors. Excessive or poorly designed stimulation can induce maladaptive plasticity, reinforcing unwanted patterns or interfering with natural functions. This is observed in some chronic pain conditions and movement disorders. In BCI, careful calibration is required to ensure adaptation remains beneficial. Another critical factor is attention. Early in BCI use, attention networks are heavily engaged. Users must consciously focus on controlling neural activity. As plasticity progresses, control becomes more automatic, freeing cognitive resources. This transition mirrors skill acquisition in natural motor learning. However, when interfaces are complex or unstable, attention demands remain high, limiting scalability. Long-term embodiment also depends on emotional and motivational systems. The brain integrates devices more readily when outcomes are rewarding and meaningful. Dopaminergic signaling reinforces successful control patterns, accelerating learning. Conversely, frustration and unpredictability slow adaptation. This interaction between effective neuroscience and BCI design is increasingly recognized as a determinant of success. As BCIs move beyond medical applications into augmentation, neuroplasticity becomes a double-edged sword. Enhancements that alter sensory resolution, memory access, or cognitive speed could reshape neural circuits in ways that affect identity and behavior. These changes would not feel artificial to the user, they would feel natural, because the brain experiences its adapted state as normal. By the end of this section, a central insight emerges. The boundary between human and machine is not defined by hardware. It is defined by plasticity. The brain does not ask whether a signal is biological or artificial. It asks whether it is reliable, meaningful, and useful. If those conditions are met, integration follows. In the next section, we will examine the systems that enable this integration at scale. How do implanted devices communicate wirelessly? How is power delivered safely inside the body? How do engineers design systems that can operate for years without failure inside living tissue? This is where neuroscience meets bioengineering at the most practical and unforgiving level. Section 5. Inside the living circuit. Power, wireless communication, and survival of machines in the brain. For a brain-computer interface to function beyond a laboratory demonstration, it must solve a problem that has defeated countless medical technologies: how to operate continuously inside living brain tissue without harming it. The brain is not an inert environment. It is warm, wet, electrically active, chemically aggressive, and constantly moving at microscopic scales. Any implanted system must survive this environment, while maintaining precision measured in microvolts and milliseconds. At the core of every implanted BCI is a paradox. The system must be powerful enough to record, process, and transmit vast amounts of neural data, yet gentle enough to avoid heating, damaging, or disrupting neural tissue. Unlike external electronics, implanted devices cannot rely on large batteries, active cooling, or frequent maintenance. Once implanted, they must function autonomously, often for years, without direct access. Power delivery is therefore one of the most fundamental constraints in brain-machine integration. Neurons are exquisitely sensitive to temperature. Even a rise of 1 to 2 degrees Celsius can alter firing patterns or cause irreversible damage. This places a strict upper limit on power consumption. Every transistor switching inside an implant generates heat, and that heat must dissipate through brain tissue that has limited thermal conductivity. Early implanted systems relied on wired power delivery, with cables passing through the skull. While effective in controlled settings, this approach carries unacceptable risks for long-term use. Openings through the skull create infection pathways, mechanical stress points, and limitations on mobility. For BCIs to scale beyond clinical trials, power must be delivered wirelessly. Wireless power transfer introduces its own challenges. Electromagnetic fields can induce currents in tissue, interfere with neural signals, and generate heat. Engineers must carefully select frequencies, power levels, and coupling methods to balance efficiency and safety. Inductive coupling, similar to wireless phone charging, is commonly used for shallow implants. However, efficiency drops rapidly with distance, making it difficult to power deeper systems. Some advanced implants incorporate rechargeable microbatteries, allowing intermittent wireless charging rather than continuous power transfer. These batteries must be biocompatible, leak-proof, and capable of thousands of charge cycles without degradation. Battery failure inside the brain is not an option. As a result, battery chemistry, encapsulation, and charging protocols are subjects of intense research. An alternative approach is energy harvesting. The brain produces constant physiological motion, blood flow, and chemical gradients. Experimental systems attempt to convert these into usable electrical energy through piezoelectric or electrochemical mechanisms. While promising, harvested energy remains insufficient for high-bandwidth neural recording. For now, hybrid systems combining harvested energy with wireless power remain experimental. Power efficiency is not solely a hardware problem. Signal processing architecture plays a critical role. Transmitting raw neural data wirelessly requires enormous bandwidth and energy. To reduce this burden, modern implants perform on-device processing. Signals are filtered, compressed, and partially decoded before transmission. This shifts computational load from external systems to the implant, reducing data rates, but increasing local power consumption. This trade-off has driven the development of ultra-low-power neuromorphic processors. These chips mimic neural computation, using event-driven architectures that consume energy only when signals occur. By aligning computation with neural dynamics, neuromorphic systems achieve orders of magnitude improvements in efficiency compared to traditional processors. In effect, the implant begins to resemble a synthetic neural structure operating alongside biological neurons. Wireless data transmission presents another layer of complexity. The skull attenuates radio frequency signals, and brain tissue absorbs energy. Communication protocols must operate within narrow frequency windows that minimize absorption and interference. Latency must remain low to preserve the sense of agency, while error rates must be extremely low to avoid misinterpretation of neural signals. Security is a non-negotiable requirement. Wireless BCIs transmit information directly related to intention and action. Unauthorized access is not merely a privacy issue, it is a safety issue. Encryption, authentication, and fail-safe mechanisms must be implemented within severe power constraints. Unlike smartphones, implants cannot afford constant cryptographic computation. Security must be efficient, robust, and resilient to failure. Encapsulation is another critical factor. Implants must be isolated from the brain's ionic environment while allowing electrical interaction through electrodes. This requires multi-layer barriers that prevent moisture ingress and corrosion. Even microscopic defects can lead to gradual failure over time. Hermetic sealing techniques borrowed from aerospace and cardiac implants are adapted for neural devices, but the required miniaturization pushes existing technologies to their limits. Mechanical durability is equally important. The brain moves relative to the skull with every heartbeat and head motion. Implants anchored rigidly to the skull experience shear forces that can damage tissue or the device itself. Flexible interconnects and strain relief structures are essential to accommodate this movement. Some designs decouple recording electrodes from processing units, allowing each component to move independently. Long-term reliability is the ultimate test. Neural implants must operate for years without recalibration, repair, or replacement. Electronics degrade over time. Materials fatigue, signal quality drifts, biological responses evolve. Designing systems that remain functional under these conditions requires predictive modeling of failure modes and conservative safety margins. A crucial realization in recent years is that implants must degrade gracefully. Complete failure is unacceptable. Systems must detect anomalies, reduce functionality if necessary, and preserve core operations. For example, if high-bandwidth decoding fails, basic communication should remain possible. This requires hierarchical system design, with multiple layers of redundancy. Regulatory and ethical constraints further shape implant design. Medical-grade devices must meet stringent safety standards. Every component, from solder joints to firmware updates, must be validated. This slows innovation but ensures reliability. As BCIs move toward enhancement applications, regulatory frameworks struggle to keep pace, creating uncertainty around acceptable risk levels. By the end of this section, it becomes clear that the brain-machine interface is not a single device, but an ecosystem. Electrodes, processors, power systems, communication links, and biological tissue form an inseparable whole. Failure in any component compromises the entire system. This engineering reality leads directly to the next question. If we can build systems that survive inside the brain, what happens when they scale? What happens when thousands or millions of neurons are connected simultaneously? How does bandwidth, decoding, and plasticity behave at scale? And where do current technologies fundamentally break down? These questions define the frontier of brain-computer interfaces and lead us into the next section. Section 6. The scaling barrier. Why connecting more neurons is not just an engineering problem. As brain-computer interfaces mature, a critical truth emerges that reshapes the entire field. Scaling is not linear. Adding more electrodes does not simply increase information. It fundamentally changes the behavior of the system. What works for dozens of neurons can fail catastrophically when expanded to thousands. What appears feasible at small scales encounters biological, computational, and physical ceilings that no amount of engineering optimization can bypass. The human brain contains approximately 86 billion neurons, connected through trillions of synapses. Even the most advanced BCIs interface with only a microscopic fraction of this system. Yet even this fraction presents overwhelming complexity. Recording from one neuron generates data. Recording from 1,000 neurons generates interactions. Recording from 1 million neurons generates emergent dynamics that cannot be predicted by extrapolation. At small scales, neural signals appear interpretable. Researchers can associate firing patterns with specific movements or intentions. As scale increases, signals become entangled. Neurons do not operate independently. They participate in overlapping functional assemblies that change on millisecond timescales. Scaling transforms decoding from a pattern recognition problem into a systems-level inference problem. One of the first barriers encountered is bandwidth. Each neuron can fire up to hundreds of times per second. Recording spikes from thousands of neurons produces data streams measured in megabits per second. Scaling to millions pushes data rates into regimes comparable to high-speed telecommunications networks. Transmitting this data out of the skull, processing it in real time, and returning meaningful output becomes a logistical impossibility without aggressive compression and abstraction. However, compression introduces loss. Neural information is not uniformly distributed. Some spikes are critical, others redundant. Determining what can be discarded without losing meaning requires deep understanding of neural coding, and understanding that remains incomplete. The brain does not encode information using a single universal strategy. Different regions use different temporal, spatial, and population-based codes. Scaling forces BCIs to confront this heterogeneity directly. Another barrier is signal interference. As electrode density increases, electrical fields overlap. Signals from adjacent neurons contaminate each other. This problem, known as crosstalk, worsens as electrodes are packed closer together. Beyond a certain density, adding more electrodes yields diminishing returns or even degrades overall signal quality. This is not a flaw of fabrication. It is a consequence of Maxwell's equations operating in conductive biological tissue. Biology imposes additional constraints. The brain cannot tolerate unlimited foreign material. Increasing electrode count increases tissue displacement, inflammation, and immune response. Even ultra-thin, flexible electrodes provoke biological reactions when scaled massively. The foreign body response does not scale gracefully. It accelerates. At high densities, glial scarring can isolate entire electrode arrays from neural tissue, rendering them ineffective. Scaling also amplifies non-stationarity. Neural representations drift continuously due to learning, fatigue, emotional state, and environmental context. With a small number of channels, decoders can adapt. With thousands, adaptation becomes unstable. Updating one part of the model can destabilize others. This creates a moving target problem, where the decoder is always chasing a brain that is reorganizing itself in response to the interface. Computational complexity grows even faster. Decoding interactions among thousands of neurons requires models with millions or billions of parameters. Training such models in real time under strict latency and power constraints pushes current AI hardware beyond its limits. Even with specialized accelerators, the energy cost of large-scale decoding threatens thermal safety. This leads to a crucial shift in thinking. Scaling BCIs cannot rely on raw data acquisition. Instead, it must rely on hierarchy. The brain itself does not operate as a flat network. It is organized into layers, modules, and functional loops. Effective BCIs must respect this architecture rather than attempting to bypass it. Hierarchical interfaces aim to interact with higher-level representations rather than individual neurons. Instead of recording every spike, they target population dynamics, oscillatory states, and low-dimensional manifolds that capture essential information. This approach dramatically reduces bandwidth requirements while preserving meaning. However, identifying these representations requires deep insight into neural computation, not just better sensors. Another scaling strategy is selective interfacing. Rather than connecting everywhere, BCIs focus on strategic nodes, regions where information converges or diverges. Motor cortex, sensory cortex, and association areas act as bottlenecks through which many signals pass. Interfacing at these points yields disproportionate influence over behavior. This mirrors how small lesions can have large effects, revealing structural leverage points in neural networks. Yet even selective strategies face limits. The brain's architecture evolved for biological communication, not digital access. Signals are distributed, redundant, and context-sensitive. There is no central bus, no master clock, no addressable memory. BCIs must infer structure from behavior, a process that becomes increasingly uncertain as scale grows. Scaling also exposes temporal limits. The brain operates on multiple timescales simultaneously, from microsecond ion channel dynamics to seconds-long cognitive states. BCIs that scale across spatial dimensions must also scale across temporal ones. Capturing fast spikes without losing slow contextual modulation is a non-trivial challenge. Many current systems sacrifice one for the other. At large scales, the concept of decoding itself begins to break down. Instead of translating neural activity into commands, BCIs may need to function as coprocessor systems that influence neural dynamics rather than explicitly interpreting them. This represents a shift from communication to modulation. The interface becomes less like a translator and more like a regulatory system. This shift raises profound implications. Modulating neural dynamics at scale risks unintended consequences. Small perturbations can cascade through networks, producing emergent effects that are difficult to predict or control. The brain is a nonlinear system operating near criticality. Scaling interaction increases the risk of destabilizing this balance. Information theory provides a sobering perspective. There are theoretical limits to how much information can be extracted from a noisy channel. Neural tissue is an extremely noisy channel. Increasing channel count does not increase capacity indefinitely. Beyond a point, noise dominates. This suggests that whole brain readout, in the sense imagined by popular culture, may be fundamentally impossible. Yet impossibility does not mean irrelevance. Even limited access can have transformative effects. Restoring communication, movement, or sensation does not require full brain access. It requires targeted, meaningful interaction. Scaling must therefore be guided by application, not ambition. By the end of this section, a critical understanding solidifies. The future of brain-computer interfaces will not be defined by how many neurons we connect, but by which neurons, how, and for what purpose. Scale without structure leads to failure. Structure without scale limits impact. Navigating this tension defines the frontier of the field. This realization forces a confrontation with the final and most difficult questions. If BCIs can scale to meaningful levels, what are the consequences for identity, autonomy, and society? Who controls the interface? Who owns the data? And how does the definition of being human change when cognition itself becomes a technological domain? Those questions define the next phase of this documentary. Section 7. When technology touches thought, cognition, identity, and the question of control. As brain-computer interfaces move beyond motor restoration and sensory substitution, they enter territory that neuroscience has historically approached with caution. Cognition itself. Cognition is not a single function. It is the emergent result of perception, memory, attention, emotion, prediction, and decision-making operating across distributed neural networks. Interfacing with these networks is fundamentally different from interfacing with muscles or sensory receptors. It alters not just what a person can do, but how a person experiences themselves. The first misconception that must be dismantled is the idea that thoughts exist as discrete entities waiting to be read. Cognition does not occur in isolated neurons or localized thought centers. It arises from coordinated activity across large-scale networks that span the cortex, thalamus, basal ganglia, and limbic system. These networks are dynamic. Their configuration changes depending on context, intention, and internal state. Any interface that attempts to interact with cognition must operate within this fluid architecture. Early cognitive BCIs focus on attentional and decision-related signals. These are not thoughts in the philosophical sense, but measurable neural correlates of cognitive states. For example, sustained attention produces characteristic oscillatory patterns in frontal and parietal regions. Decision-making involves transient activity in prefrontal and motor planning areas as the brain accumulates evidence and commits to an action. These signals can be detected, predicted, and in limited cases influenced. The ability to detect cognitive states introduces a subtle shift in agency. When a machine can infer whether a user is attentive, fatigued, or uncertain, it gains the capacity to adapt its behavior accordingly. In medical contexts, this can be beneficial. BCIs can adjust stimulation to suppress pathological activity or enhance impaired cognitive function. In non-medical contexts, the implications are far more complex. Agency is not simply the ability to act. It is the subjective experience of being the author of one's actions. Neuroscience has shown that this experience is constructed. The brain generates actions before conscious awareness, then retrospectively attributes intention. BCIs intervene directly in this process. When a machine assists, modifies, or anticipates an action based on neural signals, the boundary between voluntary and assisted behavior becomes ambiguous. This ambiguity is not hypothetical. Users of advanced BCIs often report a gradual shift in how actions feel. Early use involves deliberate effort. Later use feels automatic. Eventually, actions initiated through the interface feel indistinguishable from natural actions. From the brain's perspective, control is control, regardless of the pathway. This raises a fundamental question. If an action is partly shaped by an algorithm, who is responsible for it? Responsibility becomes even more complex when BCIs provide cognitive enhancement rather than restoration. Enhancing memory retention, accelerating decision-making, or modulating emotional responses requires interacting with neural circuits that define personality and identity. Identity is not stored in a single region of the brain. It emerges from stable patterns of cognition, emotion, and behavior over time. Altering these patterns alters the self. Neuroplasticity ensures that repeated interaction with cognitive BCIs leads to long-term changes. These changes may not feel artificial. The brain integrates new capabilities as part of its normal functioning. Users do not experience themselves as augmented. They experience themselves as improved. This normalization complicates ethical assessment. If enhancement feels natural, where does one draw the line between therapy and transformation? Control is another critical axis. BCIs rely on algorithms trained on neural data. These algorithms are not transparent. Deep learning systems, in particular, operate as high-dimensional function approximators whose internal representations are difficult to interpret. When such systems influence cognitive processes, understanding causality becomes challenging. Did a decision arise from the user's intention, the system's bias, or the interaction between the two? Closed-loop cognitive interfaces intensify this issue. These systems monitor neural activity, predict outcomes, and deliver stimulation to steer brain states toward desired targets. In clinical settings, this is used to suppress seizures or stabilize mood disorders. However, the same principles could be applied to optimize attention, reduce anxiety, or enhance focus. The distinction between assistance and manipulation becomes increasingly subtle. Neuroscience provides no clear boundary between influence and control. The brain is constantly influenced by internal and external signals. Language, social cues, and environmental design already shape cognition. BCIs simply operate at a deeper level, closer to the neural substrate. This depth amplifies both effectiveness and risk. Another dimension of identity arises from continuity. A person's sense of self depends on the continuity of experience over time. If BCIs introduce persistent changes to cognitive processing, they may alter this continuity. Gradual change may go unnoticed, but accumulated effects can be profound. Long-term studies of implanted cognitive devices are limited, leaving many questions unanswered. Privacy takes on a new meaning in this context. Neural data is not like other biometric data. It reflects patterns of attention, intention, and internal state. Even if raw thoughts cannot be read, probabilistic inference can reveal preferences, tendencies, and vulnerabilities. Protecting this data is not simply a technical issue. It is a question of cognitive sovereignty. Cognitive sovereignty refers to the right to mental self-determination. As BCIs become more capable, ensuring that users retain ultimate control over how their neural data is used and how their cognition is influenced becomes essential. This requires not only technical safeguards, but legal and ethical frameworks grounded in neuroscience rather than speculation. Scientific research also confronts a methodological challenge. Studying cognition through BCIs risks altering the very processes being measured. Observation becomes intervention. Experimental results may reflect the interaction between brain and interface rather than intrinsic neural function. This complicates interpretation and demands new experimental paradigms. Despite these challenges, cognitive BCIs offer unprecedented insight into how the brain constructs experience. By observing how neural networks adapt to artificial pathways, researchers gain clues about the fundamental principles of cognition. These insights feed back into neuroscience, AI, and philosophy, creating a feedback loop between understanding and application. By the end of this section, it becomes evident that the most transformative impact of brain-computer interfaces may not be technological but conceptual. They force a reevaluation of agency, responsibility, and identity grounded in empirical neuroscience rather than intuition. The brain does not resist integration with machines because it lacks a sense of purity. It adapts, because adaptation is its defining property. The remaining question is no longer whether humans can connect their brains to machines, but how society will manage the consequences. Technology does not evolve in isolation. It enters legal systems, economic structures, and cultural norms. The final sections of this documentary will address these systemic implications and the boundaries that science itself imposes. Section 8. Restoration or enhancement, where neuroscience tries and fails to draw a line. From the earliest days of brain-computer interface research, the field has justified itself through medicine. Restoring lost function is ethically defensible, socially acceptable, and scientifically tractable. Helping a paralyzed patient regain movement, enabling communication for individuals with locked-in syndrome, or suppressing pathological neural activity in epilepsy presents a clear moral narrative. In these contexts, BCIs are corrective technologies, returning the brain closer to a prior baseline. However, neuroscience itself undermines the clarity of this narrative. There is no single baseline for the human brain. Neural function varies widely across individuals, across developmental stages, and across contexts. What counts as normal is a statistical construct, not a biological constant. When BCIs restore function, they do not rewind the brain to an earlier state. They introduce a new configuration, one that the brain must adapt to and incorporate. This becomes evident when examining neuroplastic outcomes in long-term BCI users. Restorative interfaces rarely replicate original biological pathways. They create alternative routes for control and perception. The brain reorganizes around these routes, often producing capabilities that did not exist prior to injury. From a neuroscientific perspective, restoration is already a form of enhancement. Consider advanced prosthetic control. Modern BCIs allow users to control robotic limbs with degrees of freedom exceeding those of natural limbs. Sensors can detect forces and angles beyond human sensory resolution. When feedback is integrated effectively, users develop a level of precision and endurance that exceeds biological norms. At what point does restoration become augmentation? The same ambiguity applies to sensory BCIs. Cochlear implants do not restore natural hearing. They replace it with an artificial encoding optimized for speech comprehension. Over time, the auditory cortex reorganizes to interpret this signal efficiently. Many users outperform individuals with normal hearing in noisy environments. The brain adapts not to recover what was lost, but to exploit what is available. Cognitive BCIs further destabilize the boundary. Devices designed to compensate for memory impairment often rely on predictive algorithms that anticipate recall needs. These systems can reduce cognitive load, improve task performance, and enhance learning speed. Even when introduced as therapeutic aids, their effects extend beyond restoration. The brain learns to rely on the interface, altering cognitive strategy. Neuroscience provides no principled way to distinguish enhancement from compensation. All neural interfaces alter signal flow, plasticity, and network dynamics. Whether these changes are framed as therapeutic or augmentative depends largely on social context rather than biological reality. This ambiguity becomes more pronounced as BCIs integrate with artificial intelligence. AI systems do not simply relay neural signals, they interpret, optimize, and predict. In doing so, they introduce computational capacities that exceed biological constraints. Memory retrieval can become instantaneous. Decision support can operate at scales of complexity impossible for unaided cognition. Even if the interface is initially deployed to address a deficit, its long-term effects reshape cognition beyond baseline function. The question then shifts from what BCIs do to why they are used. Medicine frames enhancement as ethically problematic, yet routinely accepts enhancements in other domains. Vaccines enhance immune response beyond natural exposure. Eyeglasses extend visual acuity. Education enhances cognitive capacity. From a neuroscientific standpoint, BCIs differ only in proximity to neural substrate, not in principle. However, proximity matters. Interventions that operate at the level of neural circuits have the potential to reshape identity, behavior, and agency in ways that external tools do not. This raises concerns about equity and access. If cognitive or sensoromotor enhancements are available only to certain populations, neural inequality could emerge. Unlike economic or educational disparities, neural modifications could compound over time through plasticity. There is also a risk of performance normalization. In competitive environments, enhancements tend to become expectations. What begins as optional becomes mandatory. This phenomenon is well documented in pharmacological enhancement, such as stimulant use in academic and professional settings. BCIs could accelerate this dynamic, embedding enhancement at the level of cognition itself. Neuroscience complicates regulatory efforts by revealing that enhancement is not a discrete intervention, but a process. The brain adapts continuously. A system that initially provides modest assistance can, over years of use, lead to profound reorganization. Regulators may approve a device for therapeutic use without anticipating long-term cognitive effects that extend beyond the original indication. Another critical issue is reversibility. Biological systems rarely return to prior state once reorganized. Removing a BCI does not necessarily restore original neural architecture. Learned dependencies, altered representations, and rewired networks may persist. This challenges the notion of enhancement as a reversible choice. The enhancement debate also intersects with evolution. Human brains evolved under constraints of energy efficiency, biological noise, and developmental trade-offs. BCI circumvent some of these constraints by outsourcing computation and sensing to machines. This raises the possibility of evolutionary decoupling, where cognitive capabilities advance faster than biological adaptation. From a scientific perspective, the most dangerous assumption is that enhancement can be cleanly controlled. Neural systems exhibit emergent behavior. Small changes in input can lead to large changes in output. Enhancements designed to optimize one function may inadvertently degrade others. For example, enhancing focus may reduce cognitive flexibility. Enhancing memory may increase susceptibility to intrusive recollection. Clinical neuroscience already grapples with such trade-offs. Deep brain stimulation can alleviate symptoms of Parkinson's disease while inducing changes in mood or personality. These effects are not side effects, they are manifestations of interconnected neural circuits. BCIs operating at scale will amplify these interactions. The distinction between treatment and enhancement ultimately collapses under neuroscientific scrutiny. What remains is a continuum of intervention, adaptation, and outcome. Decisions about where to intervene are therefore not scientific alone, they are societal, ethical, and political. By the end of this section, a critical realization emerges. The debate over enhancement is not about technology, but about values. Neuroscience can describe what happens when brains integrate with machines. It cannot dictate which outcomes are acceptable. That responsibility lies beyond the laboratory. The final sections of this documentary will confront this broader context. How will societies regulate technologies that reshape cognition? What legal frameworks can protect agency and autonomy? And what limits does science itself impose on how far brain-machine integration can go? Section 8. Neuroethics, Brain Privacy, and the Risk of Cognitive Surveillance. As brain-computer interfaces transition from experimental laboratories into hospitals, consumer devices, and eventually everyday environments, a new scientific and ethical frontier emerges. Neuroethics. Unlike previous technologies that captured external behavior or digital activity, BCIs interact directly with the biological substrate of thought itself. Neural signals are not merely data streams, they are manifestations of intention, memory, emotion, and identity. This creates a category of risk fundamentally different from conventional cybersecurity or data privacy concerns. When machines gain the ability to read, interpret, and potentially influence neural activity, society enters an era where the boundary between mind and machine becomes legally and philosophically ambiguous. From a scientific standpoint, neural data is extraordinarily rich. Electrical patterns recorded from the motor cortex can reveal intended movement before physical action occurs. Signals from the prefrontal cortex can correlate with decision-making processes, impulse control, and planning. Activity within the limbic system can reflect emotional states such as fear, stress, or reward anticipation. As decoding algorithms improve, particularly with deep learning models trained on large neural data sets, the resolution of inference increases. This means that even partial or noisy neural signals can be reconstructed into high-confidence predictions about mental states. The risk is not hypothetical. In controlled experiments, researchers have already demonstrated the ability to predict choices, recognize visual stimuli a subject has seen, and infer words a person intends to speak, sometimes before conscious awareness. This raises the first major ethical challenge: mental privacy. Traditional privacy laws are designed to protect observable actions, communications, and stored information. Neural data does not fit neatly into these frameworks. A brain signal is neither a spoken word nor a written message, yet it may contain more sensitive information than either. If neural recordings are stored, transmitted, or analyzed by external systems, cloud servers, AI models, or third-party vendors, who owns the data? The patient, the device manufacturer, the healthcare provider, or the algorithm that processed it? At present, no global consensus exists, and regulatory bodies are struggling to adapt existing legal structures to this unprecedented category of data. Closely related is the concept of cognitive liberty, the right to control one's own mental processes without external coercion or surveillance. In a future where BCIs are used for productivity, education, or workplace optimization, subtle forms of pressure could emerge. Employers may encourage neural monitoring to assess focus, fatigue, or emotional engagement. Governments could justify neural screening for security or law enforcement purposes. Even consumer platforms might incentivize users to share neural data in exchange for personalized services. Each step may appear voluntary, but collectively they risk normalizing a system where thought itself becomes observable and monetizable. From a neuroscientific perspective, the danger extends beyond observation to modulation. Many BCIs are bidirectional. They not only read neural signals, but also stimulate neural tissue. Electrical or magnetic stimulation can alter neural firing patterns, influencing mood, attention, or behavior. While therapeutic in controlled medical contexts, the same mechanisms could be misused. Poorly designed stimulation protocols may induce unintended plastic changes in neural circuits. Long-term exposure could reshape cognitive habits, emotional responses, or even personality traits. This is not science fiction. Neuroplasticity ensures that repeated stimulation leads to lasting changes in synaptic strength and network organization. Another underexplored risk is algorithmic bias at the neural level. AI models, trained on neural data, are influenced by the demographics, health conditions, and cultural contexts of their training populations. If BCIs are primarily developed using data from limited groups, their decoding accuracy may vary across individuals. Misinterpretation of neural signals could lead to incorrect assumptions about intent or mental state, particularly in legal, medical, or security contexts. A false inference from neural data could have consequences far more severe than a misread facial expression or erroneous text analysis, because it carries the perceived authority of biological measurement. Security vulnerabilities compound these concerns. Any device that interfaces with the nervous system becomes a potential target for hacking. Unauthorized access to a BCI could allow interception of neural data or manipulation of stimulation signals. Unlike traditional cyberattacks, the consequences here could include physical harm, psychological distress, or long-term neurological effects. Researchers have already demonstrated proof-of-concept attacks on implanted medical devices such as pacemakers and insulin pumps. As BCIs become more networked and software-driven, their attack surface expands. Neural cybersecurity is emerging as a critical scientific discipline, combining neuroscience, cryptography, and embedded systems engineering. International responses to these challenges are beginning to take shape, but progress is uneven. Some countries have proposed recognizing neurights, including the right to mental privacy, identity, and free will. These frameworks aim to prevent coercive neural data collection and unauthorized cognitive manipulation. However, enforcement remains difficult, especially in a global technology market where devices, data, and algorithms cross borders seamlessly. Without standardized protections, individuals may unknowingly surrender neural rights simply by adopting new technologies. Ultimately, this section confronts a central question of the documentary: what does it mean to be human in an era where the brain is no longer a closed system? Scientific advancement has made it possible to observe and interact with neural processes at unprecedented resolution. The same tools that restore movement to paralyzed patients and speech to locked-in individuals also carry the potential for surveillance, manipulation, and inequality. The outcome will depend not only on technological capability, but on the ethical frameworks, regulations, and societal values established now before brain-machine interfaces become invisible, ubiquitous, and irreversible. Section 9. Military, intelligence, and strategic uses of brain-machine interfaces. As brain-computer interfaces mature from clinical instruments into scalable technologies, one domain has followed their progress with exceptional interest: military and intelligence research. Historically, every major breakthrough in communication, computation, and human-machine interaction, from radar to GPS to the internet, has been shaped by defense priorities before entering civilian life. BCIs are no exception. For military strategists, the brain represents the final and most critical bottleneck in human performance. Reaction time, cognitive load, fatigue, decision-making under stress, and coordination between humans and machines all ultimately depend on neural processing. Brain-machine interfaces offer a path to measure, optimize, and potentially enhance these processes directly at their biological source. Scientific military interest in neural interfacing did not begin with modern AI or Silicon Valley startups. As early as the Cold War, defense laboratories investigated electroencephalography to study pilot workload, vigilance, and stress. These early efforts were limited by crude sensors and analog signal processing. What has changed is scale and precision. Advances in high-density electrode arrays, real-time signal decoding, machine learning, and miniaturized electronics have transformed BCIs from passive monitoring tools into active control systems. Today, neural signals can be decoded fast enough to influence machines in milliseconds, well within operational combat timeframes. One of the most immediate military applications is cognitive state monitoring. Soldiers operate in environments characterized by extreme stress, sleep deprivation, sensory overload, and split-second decision requirements. Neurophysiological signals can reveal mental fatigue, loss of situational awareness, or impaired judgment before behavioral signs appear. Research programs have demonstrated that EEG and intracortical signals can predict lapses in attention seconds before they occur. In a battlefield context, such early warning systems could allow adaptive automation, shifting control to AI-assisted systems when human cognition becomes unreliable, or alerting command structures before errors escalate into casualties. Beyond monitoring lies direct neural control of systems. Experimental demonstrations have already shown that humans can pilot drones, robotic vehicles, and simulated aircraft using neural signals alone. In controlled laboratory settings, operators have controlled swarms of unmanned aerial vehicles through motor imagery simply by imagining movement. The scientific principle is straightforward. Neural populations in the motor cortex encode intended movement regardless of whether muscles are activated. By decoding these signals, machines can respond faster than physical interfaces allow. In military scenarios, this could reduce reaction times, enable silent control, and allow injured personnel to continue operating systems despite physical impairment. The integration of BCIs with autonomous weapons and AI decision systems introduces a new level of complexity. Modern warfare increasingly relies on human-machine teaming rather than direct human control. BCIs could allow neural signals to serve as high-level intent inputs, while AI systems handle execution. For example, a commander's neural confirmation signal could authorize a predefined action sequence across multiple platforms simultaneously. While this may increase efficiency, it also raises scientific and ethical concerns regarding decision accountability. Neural intent is probabilistic, not binary. Decoding algorithms infer likelihoods, not certainties. In high-stakes military environments, misinterpretation of neural signals could have irreversible consequences. Another area of intense research is neural augmentation. Military organizations have long explored pharmacological and technological methods to enhance endurance, attention, and resilience. BCIs introduce the possibility of direct neuromodulation. Electrical or magnetic stimulation of specific brain regions can alter alertness, learning rate, and emotional regulation. Transcranial stimulation studies have shown temporary improvements in target detection, working memory, and reaction speed. When combined with closed-loop BCIs that monitor neural state in real time, stimulation can be dynamically adjusted to maintain optimal cognitive performance. From a neuroscientific perspective, this exploits neuroplasticity, the brain's capacity to adapt to train and reinforce desired neural patterns. However, augmentation is not without cost. Repeated neuromodulation may induce long-term changes in neural circuitry that persist beyond the operational context. Alterations in emotional regulation, stress response, or risk perception could affect post-service mental health. Unlike traditional equipment, neural modifications cannot be simply removed or returned to storage. This introduces unprecedented challenges for military medicine, veteran care, and long-term neurological monitoring. Intelligence agencies are also investigating BCIs for information acquisition and analysis. Rapid processing of vast data streams is a core challenge in modern intelligence work. Neural interfaces could theoretically identify subconscious recognition signals, tiny neural responses that occur when a person recognizes a familiar pattern, face, or anomaly even before conscious awareness. Experiments in neuroscience have demonstrated that recognition-related signals can be detected within hundreds of milliseconds. Applied at scale, such techniques could accelerate threat detection, pattern recognition, and anomaly spotting. Yet this blurs the line between assistance and extraction, raising concerns about involuntary cognitive disclosure. Perhaps the most controversial dimension is cognitive warfare. Traditional warfare targets physical infrastructure and human bodies. Cognitive warfare targets perception, decision-making, and belief formation. BCIs expand the theoretical toolkit for such operations. If neural systems can be influenced through stimulation, sensory substitution, or feedback loops, adversaries may seek to disrupt cognition rather than destroy hardware. Even non-invasive methods, such as exploiting neural entrainment through audiovisual stimuli, already demonstrate how brain rhythms can be influenced externally. Coupled with BCIs, these effects could become more targeted and measurable. From a strategic perspective, BCIs represent a new arms race. Nations that achieve reliable, secure, and ethically deployable neural interfaces could gain asymmetric advantages in command, control, and human-machine coordination. This has triggered significant investment from defense agencies worldwide. Research initiatives focus not only on capability development, but also on countermeasures detecting unauthorized neural interference, protecting implanted systems from cyberattack, and ensuring signal integrity under hostile conditions. Security remains a critical scientific challenge. A compromised BCI in a military context is not merely a data breach. It is a direct vulnerability in a human nervous system. Interference with neural signals could degrade performance, induce confusion, or cause physical harm. Designing cryptographically secure, fault-tolerant neural interfaces requires interdisciplinary expertise spanning neuroscience, hardware engineering, cybersecurity, and applied mathematics. Unlike conventional systems, failures cannot always be mitigated through redundancy or shutdown, because the human brain remains continuously active. International law has yet to catch up with these developments. Existing conventions governing weapons and warfare do not account for technologies that operate inside the human nervous system. The distinction between weapon, tool, and enhancement becomes blurred when neural interfaces alter cognition itself. Scientific advisory bodies warn that without proactive regulation, military BCIs could outpace ethical oversight, leading to deployment before long-term consequences are understood. This section underscores a recurring theme of the documentary: technology evolves faster than the frameworks designed to govern it. Brain-machine interfaces offer military organizations unprecedented insight into and influence over human cognition. Whether these capabilities are used to protect lives, enhance coordination, or exert control depends on decisions being made now in research labs, policy rooms, and defense committees. The brain, once considered an inviolable domain, is becoming a strategic terrain, one where the next generation of conflict may be fought not only with machines, but within the neural circuits of the human mind itself. Section 10. The future of human identity in a neural world. As brain-computer interfaces move from experimental technology to integrated elements of daily life, they challenge one of the most fundamental questions of human existence: what does it mean to be human? For millennia, identity has been tied to continuity of mind, perception, and memory. It has been shaped by the unbroken thread of experience flowing from past to present. BCI, by allowing direct interaction with cognition itself, introduce a variable that evolution never accounted for: the ability to alter thought, memory, emotion, and perception through external, artificial means. Neuroscience provides the foundation to understand these changes, yet it also makes clear that they are neither trivial nor easily reversible. At the core of identity lies neural plasticity, the brain's capacity to reorganize itself in response to experience. As explored in earlier sections, plasticity enables the integration of prosthetic limbs, sensory augmentation, and cognitive BCIs. Over time, these systems cease to be external tools and become incorporated into the user's internal model of the self. In practical terms, the brain treats the BCI as part of the body and the mind. This integration creates a profound shift. The distinction between what is biologically human and what is technologically augmented begins to blur. Memory is particularly affected. Cognitive BCIs that provide predictive memory assistance or enhanced recall alter not only what is remembered, but how memories are stored and retrieved. Studies of hippocampal stimulation and cortical interfacing reveal that artificial reinforcement of neural circuits can strengthen some memory traces, while weakening others. As a result, the boundary between naturally encoded experience and machine-facilitated recollection becomes fluid. Over years of use, users may rely increasingly on the interfaces to maintain cognitive continuity, subtly reshaping their neural identity in ways imperceptible to conscious awareness. Perception is similarly transformed. Visual, auditory, and somatosensory BCIs can extend human senses beyond natural limits. High-resolution prosthetic vision, auditory augmentation, and tactile expansion allow humans to detect signals they could never perceive before. The neural consequence is adaptation. The brain integrates these artificial signals into its perceptual schema. Sensory boundaries once dictated by evolution are now extended by technology, yet the brain treats these extensions as natural. Consequently, augmented perception changes how humans interpret reality, interact with the environment, and even form emotional and aesthetic judgments. Emotion and affective processing are also susceptible. BCIs designed to optimize cognitive performance or therapeutic interventions can influence limbic system dynamics, altering stress response, reward anticipation, and motivational drive. Longitudinal studies of neuromodulation show that repeated interventions may produce durable changes in personality traits. From a neuroscientific perspective, this is not a flaw but a predictable outcome of adaptive plasticity. The brain learns to optimize circuits for consistent feedback, creating new stable states that redefine the individual's behavioral repertoire. Identity is further complicated by networked cognition. As BCIs become connected to cloud-based processing, AI-driven decision support, and shared neural interfaces, human thought may increasingly operate in conjunction with external computational systems. Decisions, memories, and predictions are no longer solely internally generated. They are co-constructed with machines. Neuroscience demonstrates that the brain readily incorporates predictive and supportive input from external sources, treating it as an extension of its internal processing. This phenomenon creates a hybrid cognitive system in which boundaries between human and machine are functional rather than anatomical. The societal implications are profound. If cognition, memory, and perception become augmentable, disparities in access to technology could translate directly into disparities in neural capacity. Individuals with access to high-resolution BCIs may experience accelerated learning, superior situational awareness, and enhanced creative capacity. Those without access would remain limited to an augmented biological cognition. Over time, this could produce stratified cognitive populations, challenging existing ethical, legal, and social frameworks. Legal and ethical systems must evolve to address these realities. Traditional notions of autonomy, responsibility, and consent are complicated by neuroadaptive technology. If a cognitive BCI influences decision-making, is the individual fully responsible for actions? How should society regulate modifications that are gradual, imperceptible, and integrated into subjective experience? Neuroscientific insights into plasticity, embodiment, and agency suggest that any intervention in cognition carries consequences that are deep, durable, and often unpredictable. Legal frameworks will need to account for the malleability of the human mind, not just observable behavior. Culturally, human identity may shift from being purely biological to being technologically hybrid. Art, expression, and communication could increasingly involve augmented perception and cognition. New forms of sensory experience may emerge that are only accessible through neural interfaces. Education, collaboration, and even empathy may be mediated through shared neural signals. The brain, historically limited by biological constraints, becomes a dynamic system whose boundaries are determined as much by technology as by anatomy. At the same time, neuroscience cautions against assuming total control. Plasticity is adaptive, but not infinite. Cognitive systems have limits in energy, network capacity, and stability. Overextension can lead to fatigue, maladaptive circuits, or impaired natural cognition. Effective BCI design requires careful alignment with the brain's inherent architecture, balancing enhancement with biological sustainability. The final challenge is existential. As BCIs increasingly mediate thought, perception, and memory, the question arises, at what point does an individual remain the same person? Philosophically, identity has always been fluid, yet historically change occurred through lived experience within natural limits. BCIs accelerate and magnify this process. Neuroscience shows that the brain's representation of self is continuously updated based on sensory input, motor experience, and cognitive feedback. When these inputs are partially artificial, self-representation itself becomes co-authored by machine systems. Despite these profound transformations, neuroscience offers a guiding principle: adaptation is inherent, predictable, and measurable. While human identity may shift, the brain will integrate neural interfaces in ways that optimize function and subjective coherence. Users will experience augmented cognition, expanded perception, and reshaped memory as natural, even as they cross thresholds of what previous generations would have considered distinctly human. By the end of this documentary, the scientific consensus is clear. Brain-computer interfaces do not simply augment humans, they redefine the boundaries of identity, perception, and agency. The implications span medicine, ethics, law, society, and culture. Humans are not being replaced by machines, but increasingly co-evolving with them at the level of neurons, networks, and experience itself. The final frontier of human adaptation is no longer external, it resides within the intricate, plastic circuitry of the brain, intertwined with the very technologies designed to extend its capacities.